So I'm going to go ahead and continue where we stopped last class. So last class we started talking about electric fields. So today what I'm going to do is that I'm going to show a few more examples. Now if you look at this picture here, you're going to see exactly what we've been talking about. We said that there is always going to be a source. Now, looking at this example, do you see that the source charge has a very large mass, right? So we're going to assume that the source is not moving. But the test charge, which is the smaller mass, that's the charge that is going to move, right? And this is basically the same example if you think about gravity. So if you look at the sun and the earth system, when you try to describe the sun and the earth system, because the mass of the sun is way bigger than the mass of earth, to a good approximation, we can say that the sun is not moving, right? So the sun is fixed. And then you're only interested in the force of gravity acting on the earth, right? So the earth is the object that is moving. So in this example here, my source charge, so we're going to assume that this is not moving, right? The test charge is what is going to move. So when I calculate, so again, notice that the source charge is Q, the test charge is Q naught. So the way we define this electric field is that we define the electric field. So remember that this electric field is produced by the source. So the electric field produced by the source is given by this equation. Is the electric force divided by the source charge. So again, if you remember, we said that the electric force is going to be KE. So Q naught divided by distance squared. So that's electric force. Now, if you take this electric force and you just divide by this source charge, by the test charge, then you get the electric field. So electric field is just going to be KE Q divided by distance squared. Now, so once we know what the electric field is, then I can say, okay, what is the force produced on the test charge is given by this equation. Now, this is, I hope, with a few examples. So with a few examples, you're going to see how this applies. Now, so let me go ahead and share a different screen here. Now, what if you have so let's say so if you have more than one source, what do you do? Just an example, suppose that I have a charge here. Let's call this Q1. I have a charge here. Let's call this Q2. So again, so Q1 and Q2, these are my source charges. Then what if I want to calculate the total force on this test charge Q naught? What do? I calculate the force that comes from Q1, and then I add it to the force that comes from Q2. All right? So let's suppose that the distance from Q1 to this point here, let's call that R1, and the distance from here to here, let's call that R2. Now remember that everything is positive, so when I calculate the force on my test charge due to Q1, I get a force that is pointing to the right, right? So let's calculate the total force. So the total force on my test charge, notice that this is just going to be equals to Q1 Q naught. So KE Q1 Q naught over R1 squared, and this will be in the I hat direction, plus KE Q2 Q naught over R2 squared, and this will also be in the I hat direction. Now, you see that I can write this equation as the Q naught I can write that equation like that. You see that Q naught appears in the first term and the second term. So we can factor out Q naught. And so what is the electric field produced by the two charges? So in this case, it means that the electric field E produced by source number 1 and source number 2 is equal to KA Q1 over R1 squared I plus KE Q2 over R2 squared I. Does that make sense? So going forward, each time that you want to calculate the force, the first thing that we're going to do is that we calculate the electric field from all the source charges, and then simply multiply by the charge of the test charge. I don't know if that makes sense or not. So we're going to be focusing on calculating electric field, because once I know electric field, I just multiply by the test charge to get the force on that test charge. All right. Now let me go ahead and solve a few examples. Let me do a few examples here. Now in this example, so let's assume that we have a positive charge here. This point is called point P. Let the distance from here to here equals to A. The distance from here to here equals to A. Let this charge has magnitude Q, this has a charge magnitude negative Q. So for part A, I want to calculate the electric field. So I want to calculate the electric field vector at point P, at P, and then part B, I want to calculate the force on test charge Q naught. So this problem has two parts. The first part is that I just want to calculate what the electric field at point P is. Then once I know what the electric field at point P is, once I introduce the test charge, I can then calculate the force on that, on the test charge. Now in this example, these are my source charges here. The difference here is that one is positive and one is negative, right? Now, so the electric field at point P So this is going to be, if you remember the way we calculated this, we said that each time that I'm calculating my electric field, I'm going to treat the charges as if I'm keeping just the magnitude of the charge. But then what makes the difference between the positive and the negative is that I can add a unit vector, right? I can add a vector. So let me write down this equation and then you tell me if this equation makes sense or not. So KEQ, now what is the distance from this positive charge to the point P?
2a.
It's 2a. So if you square that, you get 4. And this would be in the I direction. And then this would be plus. Now do your math and simplify this, you get negative 3/4. And this would be in the I hat. So this is my part A. Why do we end up having a negative charge? Why is the electric field end up being a negative value? Because the negative is closer, right? I have two charges, positive and negative. But remember we said that the field strength goes as 1 over distance squared. So the contribution that is coming from this positive charge is less than the contribution coming from the negative charge because my negative charge is closer to my point P. Does that make sense? Now, for part B, when I calculate the force on the test charge, again, I just take my Q naught and I multiply by my electric field. So do you see that this is going to be negative 3/4 KE Q. Now let me ask you, in what direction is Q not going to move?
Negative x direction.
Is it going to move in the negative x direction or in the positive x direction?
Negative.
Now I would say it depends, right? It depends on Q naught. If Q naught is a positive charge, right? Then it moves to the negative x direction. But if Q naught is a negative charge, then the negative times the negative gives me positive. So if Q naught is greater than 0, it's going to move to the left. And if Q naught is less than 0, it should move to the right.